because of their okay, these isotopes they form because of their environmental changes, not environmental conditions. Different temperature, different pressure, different reactions, conditions they have under certain conditions. So that is why the isotopes are produced. And if we see one example for the isotopes, or if you want to understand that the atoms of different molecules and also for their neutral stand for the atoms. For here, we see that chlorine is 35, right? So that what is not changing here in for chlorine? 35, 37, 17, 17. So which one is proton, number of proton, or atomic number, and which one is mass number? This is the atomic number, it's not changing. So this is number of protons it has. But 35 and 37, this is the number of proton plus neutron. Right? Proton plus neutron. See, this is chlorine as well. Chlorine is chlorine. But this is number of proton here at the bottom here. Okay, so at the bottom, left side corner, bottom, that is the number of protons, and top, left top is the atomic number. Okay, so we see that proton 17, oh, it's written here actually. So neutron is 18, and for here is neutron is 20. And electron is 17 and electron is 18 here for two different. Why it is so? Why it is so that electron is 18 here and electron is 17 there? Because of this negative charge. Since this is negative charge here, that means I have one extra electron. That extra electron is making it negative. Okay? But for this case, there is no extra anything, no positive, no negative. Of course, positive will not show you, only negative is shown. So that means it has the exact amount of proton and neutron, this positive and negative charge. For iron, 2 ion, that means it has 2 extra electron has been left, right? What is supposed to be 2 electron has been left. That means electron, if electron is leaving, that will give you positive charge. So it has 26 proton, and 26 proton making 26 plus positive charges. 24 electron is making 24 negative charges. So if we deduct it, 2 positive charge remaining there. Is it clear? Yeah? Everyone clear, yeah? I know it's easy thing. So above this is the chlorine is the isotopes for there. Now if we look here in the periodic table, if you look in the period, what's wrong? Yeah. What is going to be? See? What's the problem now? Okay.
There's no other way that I don't see anything else. Yeah. Okay, so hopefully it's stable now. Right, so for all the elements here on the periodic table, and it has a very interesting property actually. So this is the group 1, right? Group 2, and this way we go to the until this group 18. So yeah. Now everywhere is open. You can look at any place. Okay. So group 1 is the alkali metal, and it is giving us sodium. I mean whatever. Okay. So here at 18, group 18, do you know what is the elements here? What do you call it? Sorry? Yeah. Something I heard. Noble gases, exactly, right? So why do you call it noble gas? Why do you call it noble gas, online friends? They don't want to react. And another interesting thing for the noble gas that everybody wants to be like them, right? Everyone wants to be like them. How? Either by shedding the electron or by gaining electrons. And that is how they will form the bonding. Anyway, so here the isotopes. Okay, for any of the elements you see here, everybody has isotopes, and some of them has hundreds of them isotopes. Okay, so let's say for chlorine, the isotopes are here 35 and 17, right? Just now we have seen it. So is there any changes here? Do you see? Is there any changes we see here? Atomic number and mass numbers. Yes, it's flat. So the conventional system of showing it is the atomic number should be on the left bottom, right? Left side bottom. And the mass number should be on the top, okay? Relative atomic mass. So the relative atomic mass now is atomic weight and average atomic mass, because they have many different type of isotopes, right? Many different isotopes. So which one do we consider is the total number of mass of that atom? What you can do is we take the whole of them, take the average. That is the best way, of course. Otherwise, you will not get the perfect one. So get all of them, and then do you think that you can finish today? Okay, I'll go a bit fast because I understand that many of you already know quite much of it. So the average atomic mass, that is because of their isotopes. Isotopes have different total mass, right? Total mass, but the atomic number is same, but atomic mass is different. So that is why we will take all of the isotopes, their mass, and then we take the average of it. So that is how we will get the average relative atomic mass. And from here, it will be denoted as AR, that is relative atomic mass, which is a function of the total percent of abundance. Percent of abundance means how many percent of that isotope is formed in the nature. Not all the isotopes are same. One is 1%, 2%, 5%, 10%. Man, one with that's prominent one, that will be like 60, 70, 80%. And there will be the rest are 1, 2, 3, 4%. So we will take the percentage of abundance of that isotope. We are going to the example now. And I mean, just next slide, we'll have the example. And the atomic mass. We multiply by that atomic mass of that percent, the isotope that we are taking, right? And this is a summation mark. This is a summation mark. So percentage times the atomic mass of this plus the next percentage plus the atomic mass of it. In that way, it will continue. If it is hundreds, we will do the hundreds of them in that way. Okay. So this is one of the example, like chlorine. Just now we have seen one is 37 and it is 35, right? For 35 is 75.91% chlorine, percentage of abundance. That means in the nature, 75.91% of the chlorine that we get is the chlorine 35. All right, out of 100. Chlorine. Where do you know where do you get the chlorine from? Pool. Swimming pool. Swimming pool. No, that is you are giving them chlorine to kill the bacteria there. You are not getting it from there. Chlorine is gas. Chlorine is gas. You can get some of it from the volcanoes, some from the other sources. Yeah, but okay. So when we are getting it from the nature, 75 or 76% of it is 35, chlorine 35. The rest 24% is chlorine 37. All right. So if I tell you that okay, chlorine is 35, will it be correct? It is not correct because I am not considering 24% of that, only considering that 76% chlorine, right? So I have to come in between to form and get the average of it. How do we get the average? Just like in the previous slide, we learned that AR, percentage of abundance, times the molecular weight of this, right? Divided by percentage of abundance. So 35 times the percentage of abundance is 76%, exactly 75.91, plus the summation means this plus, plus, plus. So if it was not chlorine, if it was something else, and it has 10 of these different isotopes. It has 10 of these different isotopes, yeah? So what do you do? We add it 10 times regarding the percentage of abundance of that isotope, right? And divided by the total abundance. Okay, so another, we just now we have found the percentage of abundance. How do you find the percentage of abundance? And then relative atomic mass to find out what is the atomic mass that we call. But there is another problem that in a composition, in a chemical compound, right? In a chemical compound, just now I say H2O, HCl, H2SO4, which is sulfuric acid. So in that chemical compound, I want to know how much percentage of one of the molecule is there, or one of the element is there, better to say. Right? What is the element? Percentage of element is there for magnesium oxide. This is magnesium oxide. I want to know how many percent of magnesium is in this compound. Or in that case, you can ask, okay, H2O. I want to know how much percentage of hydrogen is there. Or let's say H2SO4, right? So I want to know how much percentage of oxygen is in H2O. Is in H2O. So very specific. I want to know how much percentage of magnesium in this magnesium oxide. I want to know how much percentage of hydrogen in this water. I want to know how much percentage of oxygen in this sulfuric acid. So how do you know? How do you find it? We get the total mass and of this compound, and then we want to know the mass of what element. We get the mass for this times 100%. So that will be the percentage. That is the percentage composition for that element or that chemical, you can say, or better to say, that element in that compound. So 60.3% of magnesium is in magnesium oxide. So rest is almost 40% or 39.7% is oxygen, right? But looking at it, can we tell how many percentage? It looks like 50-50, right? But it depends on the mass of that element. Empirical formula and molecular formula. Empirical, so this is now we are coming to the empirical formula. This is the simplest. There are two types of two ways to express the molecule. I mean, the symbol of the compounds, chemical compounds. One is empirical formula, another is molecular formula. Empirical formula is the simplest way of showing the molecules or elements attached in the molecule. Like, I do not care how many of them there, exact ratio, 1:2, 2:5, 3:7, I don't care. I just want to know that they are hydrogen, nitrogen, sulfur, oxygen, they are, all of them are here, and they are in some arrangement, right? So that is the empirical formula, the simplest way of expressing the compound of the different molecules arranged in the compound. And then the molecular formula, that is the most important thing for us. If even if the empirical formula is given to us, we will not be able to know what is the empirical, what is the compound. But if the molecular formula is given to us, we will know exactly what, I mean, directly we understand what is the compound, right? So the exact, I mean, actual, the whole number of the ratios, like carbon is to hydrogen, how many carbon, how many hydrogen in one molecule, how many oxygen in one atoms, of course, atoms in one molecule, they are distributed or arranged, so they form the compound. In that way, we know exact amount, and that is how we know that, I mean, that is the molecular formula. So the molecular, I mean, empirical formula for glucose, every day that we take the sugar, right? Every day we take it for tea, coffee, milk, whatever, chocolate. We know this one, and we are very familiar with this, C6H12O6. This is the sugar. But this is the empirical formula, same thing, CH2O. That means here carbon and oxygen, I mean, sorry, the hydrogen is twice the ratio of carbon and oxygen. That's it. The empirical formula is telling us that, right? So what is the, I mean, why empirical formula? I mean, somebody can ask the question that if we need molecular formula, why do we bother about the empirical formula, right? Because if we try, I mean, we don't need to go to that, but if we try to formulate or isolate one chemical from some kind of sources, then we go through this empirical to molecular formula. Success is not that easy, right? Success needs so many dedication. So the scientists, they go through that way. They find out the empirical formula and then try to go to the molecular formula that way. Right. So calculate the empirical formula of an oxide of lead which contains 86.6% of lead. Now, 86.6% of lead is there. The rest is what? The rest is oxygen, right? Of course, the rest is oxygen. So we don't need to show it that way, but we understand that this is the oxygen. If it were not a binary compound, if it is the 4 elements in the compound, and it will not be given to you. I mean, it will not be given that way explicitly that 5% of this, 10% of that, 20% of this, and then the rest is this. No. You have to understand that, okay, 5, 10, 15 is given, so the rest is, of course, the other material or element is there. Okay? And okay, so how do you find the empirical formula? First of all, the most important thing, we find the number of moles. Okay? We find the number of moles. I hope that you guys can see. So we find the number of moles. Okay, first of all, before that, we have to find the number of moles, we need the mass. We need to know the mass. So 86% of lead, we just consider it 86 gram. There is no harm. We are not depriving anyone. 86% lead means we consider 86.6 gram of lead we have. Let's say they didn't give us the whole number, so we consider it's out of 100 gram, 86.6%, so 86.6 gram, right? So 86.6 gram of lead we have, and then the rest is, of course, oxygen. So we find a number of moles of lead. The lead is one of the heaviest thing. So 206 number of moles, molecular weight. We divide by molecular weight, and then we find the number of moles of lead. This is the important thing that we find. And after that, we will find the simplest ratio. Okay, we'll find the simplest ratio. So simplest ratio means we divide the number of moles will be divided by the smallest number of moles among all of them. It is only here 2 of them are here, lead and oxygen. If there are 5, 10, whatever number, among them the smallest number we would take and divide. Right? So these 2, this is the smallest number, so we divide both of them, the smallest number. So we get the simplest ratio. So the ratio is 1:2. So lead is 1, oxygen is 2, right? So this is how we find the empirical formula. But to get the molecular formula, later on, we get the molecular formula. How do you get? We will divide the empirical formula by their molecular weight from the mass of the molecular mass by the empirical formula mass. We will divide and find the ratio between them, and that ratio will be used to multiply the total number of the elements in the molecule. So for, let's say that it says the CH2 relative molecular mass of the compound is 180. The CH2 is the empirical formula, right? This question is asking what is the molecular formula for us? CH2 the empirical formula, and the compound mass is 180. So how do you find it? We divide this 180 by this. What will be the mass for this? Carbon is 12. Carbon is 12. Hydrogen is 2. Sorry, 1 times 2. 2 of them are there, right? 2. So 2 hydrogen is there. And then oxygen is 16. We have rounded it off, but anyway, you can get the closest number anyway. So by this, the ratio we get 6. Since the ratio is 6, we have to multiply the whole number by 6. Yes, yeah. And this is the molecular formula we are getting, right? Okay, so once we have learned about the molecules and empirical formula, we also have to learn about this molecular formula for this chemical reactions and how are they forming, and not only the chemical reactions, but most important thing is we have to know how to balance them. Balancing is most important thing. Yeah. So magnesium chloride, iron sulfate, and these are the. Oh, it's broken because it's from the web I'm showing. What's the problem here? Yes. Good, good, good. So it should be like this. It is not here. It should be like this. It should be like this. All right. So -2, that means, and here as well, this positive charge, not here. Okay. So in this way. I hope you can find a correct one in the PDF already shared on Canvas under the module. Okay, so I was going to ask you one thing. Forgot what I was going to ask. Oh, yeah. So now here we see that magnesium and 2 chloride. Why it is 2 chloride? Why 2 chlorine? I have to add. Not chlorine actually, chloride.
Since it's 2 positive charge.
Yes. So to neutralize this 2 positive charge, and chlorine is 1, so 2 will needed to neutralize this 2 positive charge. Same goes for here. It's 2 negative charges, 1, so I need 2 of them. So this way it will go. We'll learn more about it later. And name of the common ions. Most of these we will be using later on, and it will be good if you can remember some of them. Not, I'm not asking you remember every of them, all of them. Of course, if you can, it's better. But at least some of them. Ammonium ion, acetate ion, carbonate, chlorate, chloride, cyanide, hypocarbonate, all those things. It is better that you remember some of them. All right. So it is not that you must remember, but it is good for you if you remember. It will be faster for you to understand. Of course, it takes time, but once you are okay, that you will see that you are learning very fast, or you are proceeding very fast. The number of moles. Number of moles, right? Have you seen a mole ever? Ever? Never? None of you? The rat-shaped mole, have you seen? Rat-like animal? A mole? You haven't seen
Oh,
it?
you mean the animal?
Yeah.
The mole.
Yeah.
I haven't seen it either.
Oh, okay. But don't be confused. That mole and this mole is different. Okay? This is Avogadro's Avogadro's number. And in 1 mole, that will be Avogadro's number of whatever thing you consider will be there. Right? Avogadro's number of, 1 mole of atoms, 1 mole of electron, 1 mole of proton, 1 mole of this pen, right? 1 mole of whatever you consider, anything, there will be this Avogadro's number of compounds or those things in it. So this is the mold. Number of mole is this is Avogadro's number is the mole. Whoever fits to this number is 1 mole, right? It does not necessarily have to be 1 mole of chemical thing. It can be 1 mole of oranges. We'll see later on. 1 mole of this pen, 1 mole of 1 ringgit. If it is 1 mole of 1 ringgit, how many billion of ringgit is that? How many thousands of billion of ringgit is that? This is how big the number, can you imagine? 23 zeros after 10. 23 zeros after 10. I think it will come until here if I start writing. So this is a huge number. 1 mole, this Avogadro's number is a huge number. And of course it can be found out, it can be established through the different calculation, but in 12 gram of carbon 12, carbon has, do you know how many isotopes carbon has? How many isotopes carbon has? Anyone has an idea? 3 isotopes, yes. Carbon 12, 13, and 14, right? So there are, but in that, 12 is the most prominent one, right? 12 is the most prominent one. So in the 12 gram of carbon, this Avogadro's number of carbon atoms are there. So that is why we call 1 mole of carbon means 12 gram of carbon, right? Okay. So yes, this number of moles is very important thing. One of the most important thing that we will be using every time for all the calculation in chemistry. Almost all the time we will be using this. So be comfortable, yeah? If you have any question or any inquiries about this, you can of course ask me anytime. So you see that 1 mole of orange contains this many of oranges, and 1 mole of oxygen molecules contains this many numbers of oxygen molecules. There are tricks we do, not me only, every one of us, we do, to test students whether they are attentive enough, whether they listen to us. Yeah. So sometimes we say that, okay, how many moles of oxygen atoms in oxygen molecule? Somebody will say, oh, this number of molecules. No, it's wrong. You know. So you have to be a bit attentive when you are listening to us, also when you're thinking, when you're doing the exam. So yeah. Okay, so what I was doing? Oh, 1 mole of oranges is 6 times 0.2023 times 23rd number of oranges in 1 mole of oranges. Can you imagine, how big do you think it will be? Will it cover the whole Pacific Ocean if we put this 1 mole of orange? No? Okay, Atlantic?
Maybe a swimming pool.
Okay, 1 swimming pool? That means, if you squeeze the juice of 1 mole of lemon, 1 swimming pool will be filled, yeah? But, cannot? Possible. How many of you vote for that? No? So you think it's bigger or smaller? Bigger. Not Atlantic. Maybe there's South China Sea. No? If you put 1 mole of orange at the same time, it will cover the whole Earth. It will reach 80 kilometers. 1 mole of orange. This is so huge number. 1 mole. Still 1 mole of atom. Sometimes you cannot see. It's so small. Just to put in perspective. Okay. So molar mass of sodium chloride is 58.3 gram, and we want to know how many number of sodium chloride contains individual formula. What is the question? Molar mass. Oh, yeah. So 1 mole of sodium chloride means
this many number of sodium chloride molecule, yeah, sodium chloride molecule will have this is the mass for them. Sodium and chloride, and it has 58.443 gram in for 1 mole. So in 1 mole, they are per mole, and they are 6.023 times 23rd, 10 power 23rd number of sodium and chlorine both there. Not chlorine, chloride, sodium chloride both there. Can I ask then, what is the mass of 1 mole number molecule of sodium chloride? 1 molecule. Like this is sodium chloride, 1 molecule, 1 of them. You can find, right? Easy. So 58.443 gram for this number, this many. So just for 1 of them, how many? We can find. It's very easy. And you can find, you can try, you can play around with this number. It's very interesting. So 1 mole of the things will always have Avogadro's number of molecules. 1 mole of the things. 1 mole of electron will have this many, right? 1 mole of hydrogen gas will have this many hydrogen molecule, but then there are in hydrogen or oxygen or nitrogen, there are 2 atoms, H2, N2, O2, right? So they will have double the number of atoms of 1 mole, right? Okay, so we are almost done. Later on, we'll go for the practice question. So this is the number of for formula for number of moles, and it will be very important for us to learn to know that number of moles, right, can be found from the number of particles divided by the number of Avogadro's number, which is of course this one, and for mass, that is the number of moles we can find when mass is divided by the molar mass. For gaseous particles, we will do this a bit more later on. That number of moles can be found from the PV over RT formula. That means pressure, volume. This R is the universal gas constant, T is the temperature, and of course for solution N equals C into V. For our case, our lab, we will be needing these 2 things very important, quite frequently. This one and this one. So these 2 will be using for when we use it in the lab for experiment. Examples: calculate the number of moles in 4.1 times 10 power 24 molecules of methane. Okay, and another one is 36 grams solid copper oxide, 50 milliliter of oxygen gas, and 250 sodium chloride. So all 4, that's just now we have seen that 4 different formula will be needed to use in all 4 this type of problem, right? So questions, the solutions are given already. For number 1, we just divide the number of molecules over the Avogadro's number of moles. Avogadro's number, so we find the number of moles, and we just follow the things. So it will be done. Okay, so there is a useful toolbox. You can think of it and try to relate how it is related to one another
how can it be found from one another, right? So you can later on you can try to find what is the connection between them, or if you want to find, or if you want to establish one connection from here to here, or from here to, let's say, there, is better if you can. And let me know, please. Yeah, just don't keep it yourself. If you can establish any new relation between these phenomena, do so, please, and let me know. Okay. Okay, so now we have another 40 minutes to go, 35 minutes. So I'll take 5 minutes break for today, and then we go for some of the practice questions. That will be our tutorial. I will not go through all. I'll go through some of them. Okay, so 5 minutes break. Do you have any question, anyone from online? They are unreactive, yeah. They are
No, sir, no
unreactive.
questions.
All right. Yeah. No. Yeah, yeah. Okay, okay. Don't go, don't go. I'm not done yet, yeah? Wait. 5 minutes break. And another thing is, both of my class for this unit, they have given me at 4 to 6 p.m. this semester. It's very tiring for me. Also, I know that you are also tired, but please bear with me. It's only 2 days a week, right? It's not that much. The rest of the 5 days you can enjoy. So before you come, have some coffee, tea. Okay, don't sleep.
This one that touch by that's further charging.
So how many of you this is the first semester, and how many of you are already here in swimmer for some time? Is the first semester for you? First. Oh, first time in campus. Okay. But before this, you were in Swinburne, yeah? Okay, so I think I'll start. Okay, so this tutorial one, that is mostly the same thing that we have done so far, is quite simple and is all related to what we have done and what we have talked about just now. All right, and there are some numerical problems just to test your how much you are attentive there learning, and we will be using the same this type of information or the formula that we have just now we have done, right? That will be the things that we'll be using. Oh, I didn't bring my paper. I need to take yours. Yeah. Can somebody give me some little bit of paper and put your write your name? Huh? Sorry? Yeah, and you don't have this. What is this much good paper? Any waste paper do you have?
Oh, waste paper.
Yeah. Just write your name. Later on, I will transfer it. Any used one, maybe one side you have used, another side you just have. So, okay, and now, oh yeah. So I'm not going through all the problems for this tutorial. I will go through some of them, and I will let you do the rest. But if you have any, I mean, of course, the solution will be uploaded or given next week. So every time, every week, the tutorial problem, the answer will be revealed to you the next week, right? If I forget to do so, it is already on my canvas. I just need to click in. Sometimes I forget to click in. Please remind me, right, that I need to update. And yeah, so before it is given to you the question, I mean the solution. Please let me know. Please try. You guys go and try, so it is better for you that way. So difficult this way. Okay, so directly go to the question then. Skip all those things. There are some work examples you can for your reference. Now, I'm going to the question number 1 that it says I hope that you guys can see also. Yes. Question number 1 says that the atoms of carbon-12 and carbon-14, right, are regarded as isotopes of the same element because they are so easy thing. Their proton number is 10, right? And then question number 2 says that X is an ion with 40 protons. We do not know whether it's atom or ion, but it has 40 protons, right? 41 neutrons and 43 electrons. Most likely has the following nuclear structure symbol. So 40 protons, and of course all of them is very clever.
all of them has 40 protons at the left bottom corner. So maybe all of them are potential, but 41 neutrons. So total number of molecular mass will be 41 plus 40, 40 plus 41, 48, 81. So there are two only, A and C. There are two only, the 81s, and then 43 electrons. So 43 electrons is 3 electron extra, right? More than protons. 40 protons, 43 electrons. So 40 protons will be 40 positive charge. 43 electrons will have 43 negative charge. So 3 extra negative charge on it. So that means C is the correct answer, right? Okay, so question number 3 says that assume that lead consists of 3 isotopes having the abundances and masses given below. According to this data, calculate the average atomic mass of lead. How do you do that? Average atomic mass of lead. So what we'll do is we multiply this plus this one. No, not this. So okay, we multiply this one plus this, and this, and then we get the number, right? So after we get it, there will be total mass divided by the total abundance. Total abundance. So this is the total mass we have to get, and we have done it before. I'm not trying to make it complicated. Probably it is in this way, but you know that you have to multiply with the relative isotopic mass times the total mass, right? You have to multiply this thing plus this thing. Multiply this plus this plus this, and that divided by that. So all together you will find, since this is lead, I understand that this will be 207 plus 1.18. Okay. Okay, so it is said that some information about the element radium is given in the table below. Some information is given that the relative atomic mass of radium is 186. 186, the percentage abundance of radium is closest. So now this is the inverse way it is asking. So what is the percentage of abundance for radium will be? It says that isotope of radium 185, relative isotopic mass is 185, right? And 187 is 187.0. What is the percentage abundance of radium will be? If we consider it is X, the rest is, let's say that relative isotopic mass of radium 187 is X, right? Consider is X percentage or abundance. Sorry, the abundance is X percentage. So what will be the 185 abundance or 185? It will be 1 minus X, isn't it? It will be 1 minus X, right? If we consider one is X, another one should be that means unity minus X, right? So in this way, we can find out the percent. We just use the same way to find the percentage of abundance. So the X times the radium is 107, right? X is times 187
and it will be 1 minus x times 185, and the total abundance of mass, so this is plus, is 186.2. And then if we solve this x, we will get the percentage of abundance for ring. Okay? All right. The percentage by mass of calcium in the compound calcium sulfate is approximately, okay, I want you to do this. I want you to do this. The percentage by mass of calcium in the compound calcium sulfate is approximately what? What is the percentage of calcium? What is the percentage of calcium? Tell me. Anybody? How do I do it? If you don't want to do, tell me, I do. I'm just telling you.
Find the mass.
Yeah.
Of calcium.
So there is that. Okay, so yeah, so calcium in the compound calcium sulfate. How do I find the calcium percentage of calcium?
Theoretically, go find the mass of calcium.
Yeah.
Which is 64.
Okay.
And then over that and divide it by the mass of compound.
Exactly. Good. So this is calcium over calcium sulfate, right? Times 100%. Right. This will be the formula. It is for calcium. If it is potassium, it is negative. I mean, whatever. It will be in this way, right? So calcium, Ca. So calcium is 40. Calcium sulfate should be 100, something like that. I don't know. Can you do it? Calcium is 40 plus sulfur is 32 time plus oxygen is 16 times 4. What is the total? 100 something. 64, right? 64 plus 32. 96. 96, 106. Is it?
No,
Huh? 136? 64. Oh, yeah, 136, yes. So calcium sulfate is 136. Calcium is 40, 100%. So this is how we will find the number. I don't know what is the character, but it is given at the end of the tutorial task that is given at the end. Question number 6. Do I go to this? Which of the following fertilizer contains the highest percent by mass of nitrogen? Which of them has the highest percent of nitrogen? Can you tell? Huh? Urea. Okay. This is urea. Let's say that highest percentage of nitrogen, right? Nitrogen is 14 over urea is the percent of mass is what? Urea. Percentage of mass of urea is what? This is urea. Carbon is 12, oxygen is 16, nitrogen 2 times 14 times 18, 28. So 12 plus 16 plus 28 plus 4 hydrogen is 4. What is that? I just skip one step here. It is nitrogen is 14 plus hydrogen, 2 hydrogen is 2 times 2, right? So this is how. Okay, so What is the mass? I mean, fraction here. 14, 8, 16, 32, 32, 34, 44, 44 plus 16 is 60. So it's 14 over 60 times 100%. What is the total mass? So this way, I mean, anyway, you know that, how we do it. Okay? So I don't know whether urea or ammonia. My thing, I think ammonia has the highest number of nitrogen. How do I say that? How do you know that? You see, ammonia is nitrogen and hydrogen only, and hydrogen is mass is 1, right? Hydrogen mass is 1. You don't have to judge in that way, but anyway, you have to do in this way. But as I know, probably ammonia has the highest number of nitrogen, but by percent of mass. And that is why this thing, all of them, actually ammonium nitrate is an amatol, is an essential thing for explosive development. Previously, in the World War, ammonium nitrate was the most important thing for the explosive thing. Urea as well, used sometimes by the terrorist organization, and ammonia sometimes. Okay, so now go to this number 7, that an organic compound is known to contain only carbon, hydrogen, and oxygen. The compound contains by mass 39.1% of carbon and 8.7% of hydrogen. The number of carbon atoms in the empirical formula is, what will be the number of carbon empirical formulas? Right? The compound, as it says, that it has 39%. I'm not going to do this again because this is quite a simple thing that you already know. 39.1% means gram, consider gram of carbon. So this is carbon, and hydrogen is 8.7 gram. We have to find the number of moles. We have to find the number of moles because we are going to do the simplest mole ratio. So number of moles, carbon is 12, hydrogen is 1.008. So by this way, 3.3 is 3.35, most probably around that. Not sure exactly. And this is, of course, 7.8 or something. So this way we find this is the smallest. So we have to divide by the same number of ratio to find the simplest or smallest ratio. So this is the number of moles. This is the number of moles. And this is the ratio. This is the ratio we find. So this is the ratio we find. And then this will be the empirical formula we find. What is that? Almost we find the empirical formula. Yeah? What is that?
Answer is 2.
Answer is 2. Oh, maybe. It's 2. So P should be the answer. Anyway, need to use the calculator. I didn't use the calculator. But it looks like it's 2 around. Okay, so online guys, any question, please, voice up, yeah? I cannot go, I don't have time to check your chat box. Please unmute yourself and talk. Question number 8, the same thing. I'm not going to do that again. Question number 9, interesting thing. The Avogadro's content is the same as in the number of what? Take a moment, just take a moment and think what could be and why it could be. The Avogadro's constant is the same as the number of electron in 1 gram of hydrogen, molecules in 16 gram of oxygen, atoms in 24 gram of carbon, ions in 1 liter of sodium chloride solution with concentration 1 mole per liter. Right? Okay, so you go for D, but we cannot just justify by just looking at the answer. We have to go through, or we have to go by evidence or fact. Avogadro's constant. What is the Avogadro's constant? 6.023 times 10^23. Right? This is the Avogadro's constant. Electrons in 1 gram of hydrogen. 1 gram of hydrogen. This is the hydrogen, right? 1 gram of hydrogen. 1 gram of hydrogen is how many moles of hydrogen gas? H2. Remember H2. H2, 1 gram of hydrogen. This is H2, that means it should be 0.5 moles, right? Shouldn't be? By 2, because it is 2 here. Right? So it is 0.5. 0.5. So since it is 0.5, it is 0.5 moles as well. Right? Okay, so electrons in 1 gram of hydrogen. And how many electrons in 1 gram of hydrogen? How can we find that? How many electrons in 1 gram of hydrogen? Anyone? See, still they are asking question. Oh no, long time ago. So how many electrons in 0.5 moles? 0.5 moles of what? 5 moles of hydrogen, right? Until this point is okay, yeah?
Yeah.
No, I mean, if you are confused, just let me know so I can go over it. I'm okay, no problem. So I have 1 gram of hydrogen. I have 1 gram of hydrogen, but he is saying that hydrogen, since hydrogen says that we have to understand that this is not a hydrogen molecule, I mean ion, it's a hydrogen gas. Hydrogen gas means 2 diatomic to H2. So 1 gram of hydrogen means 1/2, of course, 0.5 moles of hydrogen, right? 1 gram. If 2 gram, it would be 1 mole of hydrogen. So since 1 gram, it is 0.5 moles of hydrogen. And then in 1 hydrogen, this is hydrogen, right? This is hydrogen. And this hydrogen is having 2 electrons. Each of them has 1 electron, right? Hydrogen is 1 proton and 1 electron. This is the hydrogen molecule, right? So they have come together to form a molecule so that they can share electrons. So each hydrogen has 2 electrons. So 0.5 moles of hydrogen has times 2 electrons, which is 6 times 0 to 3 times 10^23 number of electrons. So this is the correct answer. And if you go for ions in 1 liter of sodium chloride solution with concentration 1 mole per liter, 1 mole per liter means 1 mole. 1 mole means Avogadro's number of molecules, right? So sodium chloride, when they dissociate in the water, they dissociate in this way, positive and negative both. So 1 mole of them are producing 2 moles of ions. It did not say that ions, it only say ions, it did not say positive or negative ion, right? That means if we dissociate the sodium chloride in 1 liter, 1 mole will produce 2 moles of ions. Positive, 1 mole positive, 1 mole negative. Right? So this is not the correct answer. D is not the correct answer. Okay? So, I mean, at home, please go and try the rest of the 2 and see how it will be interesting. Almost done, almost done. Wait. Question number 10 says that different quantities of nitrogen oxide are listed below. Which one contains the least number of molecule? Least number of molecule. Which one have them? Question number 10. Different quantities of nitrogen dioxide, are listed. So this one, 6 times 10 power second liter of nitrogen at 273 Kelvin and 1 atmosphere. So 270 Kelvin is 0 degree, right? Right? Okay, later on we'll talk about the SLC and STP. So liter, it is 600 liters of nitrogen. And then this is 6 times 10 power 20 of nitrogen. 600 grams, 6 moles. Which one is more bigger number? Sorry, least number. So this one, B is the least number, right? Because in 6 mole, it is 600 grams, of course, big. 600 liters, of course, is much bigger. And 6 moles still has 6.023 times 23rd number of molecules. So this one is the correct answer. This is the B is the correct answer because this is the least number. Question number 11 says, what? Question number 10, once again, it says that which one of them has the least number of molecules? Lowest number. Options A is 6 times 10 power second, that means 600 liter. 600 liter. 600 liter, of course, there is very big amount. B says that 6 times 12 power 23rd molecules. Okay, and I go for this because the rest of the C is 6 times 10 power second grams. It is already 600 gram of nitrogen, and then D is 6 moles. And for me, quickly, I found that 6 moles is still having more than B. All right, and 600 grams, I'm not going for 600 liter, but for 600 grams of nitric oxide, actually, nitrogen oxide. How many moles in 600 grams? For option C, how many moles of nitric oxide I have? How do I find it? Just divide by very tired, yeah? So I just divide it by the molecular weight of nitric oxide, which is what? Molecular weight of nitric oxide is nitrogen is 40. Yeah, good, but I want to still show how we find it. And oxygen is 16. How do you find this 14 and 16? From the periodic table, right? From the periodic table. So this is 30. So 6 times 600 by 30 is how many? 600 by 30 is 20. So this is 20 moles. 20 moles. So this is still B, right? So that is why option B is the correct answer. Number 11, it says that what is the mass of one acetic acid molecule? One acetic acid. Just now I was talking in the beginning that sodium chloride, one molecule of sodium chloride, how much is that? The same way we'll go. 1 mole of acetic acid, 1 mole of acetic acid will have Avogadro's number of molecules, right? 1 mole. Can you see? These guys are quiet here. Okay. So 1 mole of acetic acid will have 6 times 2/3 times 10 power 23rd. I will be talking about this Avogadro number of moles quite much time until you become bored. Okay, so this is 1 mole, and in 1 mole, this is number of molecules. So this is 60, right? What is the mass of 1 acetic acid molecule? 1 mole of acetic acid is, what is the molar mass of acetic acid? I forgot. 12. 24 plus 32 over plus 4. So 10, 3, 2, 5, 6. 6, yeah, 60. Okay, so 60 gram. Yeah, this many has 60 grams. So 1 is divided by 60, 60 divided by the rest. 2, 3 times 10, 20. So this is the one molecule will have this amount. Number 12, it says that volume at standard laboratory condition, 0.22 gram of carbon dioxide is equivalent to that of. Here, there's the trick. That's why I wanted to come here, because the rest are easy. Number 12 is, there is a trick here, yeah? Online, those are online, please listen. Question number 12. Volume at standard laboratory condition, SLC, we will learn later on, of 0.22 gram carbon dioxide is equivalent to that of what? And here there are many things. Sometimes you say, what is the, there was the relation. Sometimes probably will think, what is the relation? Why is this thing? 0.01 gram of hydrogen gas, molecules of ammonia, milliliter, all of the above. How? I mean, there is no, since there is no relation, right? One thing is, from this gas law, we know that at standard temperature pressure, or SLC, standard laboratory condition, right? Any gas that has the same number of moles will occupy the same space, right? Gas law. It says Charles or Boyce, I forgot, but this is gas law. Any gas has the anything. It doesn't matter how big the molecule or smaller the molecule size. If has the number of moles is same, it is going to occupy the same space. Okay, so we will see that what is the 0.22 gram of carbon dioxide is how many moles? 0.22 over 44 is, I don't know what is that. Okay, so this is the number of moles, and we have to find if all of them has the same number of moles or not. So this is the number n, and later you'll see that it has the n is same for all three. So the correct answer is D, all of them above. Okay, so this is the trick. Sometimes you have to be, you have to see in that way that what is the trick is being played. But you don't need to think too much. It is sometimes it happens. Okay, so the rest of the problem are very much doable, and you try at home. Please let me know if you have any question or any problem understanding, so that we can solve. And I'll see you next week this time. 4 p.m. Tuesday. Okay? Next week Tuesday I'll see you. Okay? Oh, by the way, since you are all here, you must have your lab coat, yeah, to come to the lab. Those who are coming to the lab, you must have your own lab coat. Yeah, you need to buy. You can purchase it online as well, no problem. So from those who are online, if any of you are coming or want to come, please let me know. Please let me know so that we can have a. Oh, Usman Zaved says the question number 10. Question number 10, once again, those who wants to go, you can go, right? Question number 10 says that the different quantities of nitrogen oxide are listed below. Which one contains the least number of molecules? Yeah. So for A, 600 liter, 600 liter. And if we try to find out the number of moles, PV equals nRT in that way, we can find, you can find out the number of moles. All right. Question number A, I mean, option A. Option B is 6 times 10 power 23rd molecules. And I voted for this one. Option C is 600 gram. Thank you. Option C is 600 grams. And 600 grams means how many moles? We have to divide by the nitric oxide, nitrogen oxide's molecular mass, which is 30. And by that way, we find 20 moles, right? And D is 6 moles. So 20 moles, 6 moles, and A is 600 liter. All are more than B. So B is the correct answer that way. Is that okay? Okay. Okay, so I'll see you next week. Take care. Bye-bye.